Hi, and welcome back to these videos on support vector machines, where in this video, we'll start talking about the use of kernels together with support vector machines. So we'll define what those are and see how they're useful together with SVMs. Right, so just a quick recap, right? SVMs, what they're doing is that they're finding the maximum margin separating hyperplane. If I have a data set that's linearly separable, it'll find this hyperplane with the largest margin to the training data, and then we'll use this hyperplane for classification, right? So on one side, we'll return the -1 class, and the other side will return the +1 class, here indicated by blue and red. And so what we saw in the last 4 videos was a rewriting of this problem into the following optimization problem, right? So via duality, we found out that we could solve this optimization problem over here, where we're maximizing over non-negative coefficients alpha I, one for each training example. This expression here, where we sum all the alpha i's and then we subtract off half of the double sum between all pairs, alpha I, alpha j, yi, yj, and then the inner product between the ith training example and the jth training example. And then we had this constraint that the sum over all the training examples of alpha I, yi had to be equal to 0. And then what we saw in the previous video was that if we can actually solve this optimization problem and find the best choice of alphas, then from that we can deduce the parameters of the best of this maximum margin separating hyperplane, where the normal vector, at least maybe an unnormalized normal vector w, would be the sum from 1 to n over the training examples, alpha I, yi, xi, and then the b could be found as basically we had to find the offset in between the closest, the blue point that is closest to the separating hyperplane and the red point that's closest to the separating hyperplane. And then we could do that using this expression here. We do the minimum over all points in the blue class, the minimum over all points with label 1, the inner product between w and xi. And similarly here, we have to take the maximum over all the red points of this inner product. We do halfway in between them and put a minus in front. Right, so if we can solve this optimization problem, then we have the parameters of this maximum margin separating hyperplane. Okay. Now, what we also talked about briefly in the previous video was from these KKT conditions, it follows that these coefficients alpha I that make up the optimal W down here, they'll only be non-zero for the so-called support vectors, which gives the name support vector machine. So what were the support vectors? The support vectors were the vectors of the points in the training data set that sit exactly on the margin, right? So the ones that actually define the margin for the maximum margin separating hyperplane. So W is will be a linear combination of only these training points. Okay, so that was an interesting observation that we had, but we didn't really see how we could exploit this for anything, right? How could we exploit this? W is only written as a linear combination of these very few training examples, in this case, just 3 training examples. So what do we use W for? Of course, we use W to make predictions on new data points, right? So when we get a new data point, the way that we make a prediction for its class is, of course, that we take the sign of the inner product between W and X plus the bias, and then this determines our prediction of the class, like in all the linear models we've seen. So, right, of course, with this definition of what W is in this optimal solution, right, we could also write out what is W. It's the sum over alpha I, yi, xi. And using, I guess, linearity of the inner product here, we could also write that as a sum now over all these training examples where alpha I is non-zero, so over all the support vectors, alpha I, yi, and then the inner product between xi and x. Okay, so now we're not using W, but we're actually summing over all these non-zero, computing each and every one of these inner products individually and summing it up with these alpha I, yi's as weights, so to say. So, of course, you could ask yourself, why would we want to do this, right? It looks much more complicated than just using W, right? In particular, and there are many more inner products we now need to compute. So this seems like a bad idea, right? What can we use this for? In particular, right, if the number of support vectors is k is 3 in this small example over here, then, and the number of features is d, then computing the sum here would take k times d time. Whereas if I just had computed my W, just written it out what it was, this would be a vector with d entries. So just computing the inner product between W and X, like we do down here, will just take order d time. Right? So it gets much slower. So it seems like a bad idea. So maybe let me try to motivate it by just recapping some slides that we saw early on in one of the previous videos on linear models. It's been quite a long time, but we had these videos on what we could do if the data is not really linearly separable, like in this example here, right? The data looks kind of easy to classify, but it's definitely not easy with using a linear model. So again, here's, I guess, the same data set, just a bit smaller with some blue points, like one class is very close to the origin, and then we have some surrounding points further away from the origin. And this is very far from being a linearly separable data set, which means that if I just run this SVM, it doesn't work here, right? There's no maximum margin separating hyperplane because there's not even a separating hyperplane. But one thing that's worth observing here is that, okay, so what we saw earlier was that, well, this data set, right, the distance from the origin could possibly classify this data well. So maybe if you could draw a circle instead of a hyperplane, then maybe you could use this to do classification. Everything inside the circle would be the +1 class, the blue class. Everything outside would be the red class or the -1 class. And then what we saw was this, in previous videos, this notion of a nonlinear transform. So what we could do here is that we say a nonlinear transform or feature transform phi is a function that maps the original points that have d features into new vectors of points that have d prime features. It could be any mapping. And then what we could do is that we could take our data and apply this feature transform first before training a support vector, this SVM. And this would give us a new data matrix X prime, which is now n by d prime instead of n by d. Then we could run this SVM optimization problem or solve it on using X prime as our data set. And then we would find for this new data set over here, we would find a separating hyperplane down here, maybe this W tilde, because if we let the feature transform, for instance, this example, right, could be the one that takes point over here has two features, x1 and x2, and then maybe just maps it to a single feature that's x1 squared plus x2 squared, right? This is the squared distance from the origin, which means that all these blue points here near the center would be mapped in the beginning of the real line, and all the red ones would be mapped further away on the real line. And now you can see that this data here is linearly separable. There's a hyperplane right here that just separates the data perfectly. So we could run SVM and find a separating hyperplane for this feature transform data. And then what we could do with this is that if we get a new point and I want to make a prediction on it, I first feature transform. So a new input point has two features, right? It belongs in the original feature space, has two features, x1, x2. I would then first feature transform them to map them to this feature space. Then I'll compute the inner product with W tilde and add the bias and take the sign. So really, in this example here with this feature transform, the hypothesis I'm really computing is I have a bias, and I have, I guess, my feature, my vector of parameters has just a single parameter, right? This is a one-dimensional case. This is W1 tilde here, the first entry of W tilde. And this would be multiplied on to this first entry of this feature transform vector, which is just x1 squared plus x2 squared. And if we think about what this is, for instance, let's say that this happens to be at the position 7 on the x-axis, then, you know, a W and a B, a W tilde and a B that matches this hyperplane here would be perhaps one with a bias of 7, and W1 tilde being -1. Because as you can see here, right, if I plug in x1 and x2 squared so that this sum is less than 7, then I'm going to get something positive, predicting the blue class over here. And if I plug in something greater, then I would get a negative number and get the -1 class. So this corresponds to this separating hyperplane over here. Okay, so right. So what we want to do with this now is to say, okay, now we want to try to combine this with feature transforms. So let's say we already know, right, that SVMs, if we solve it, the vector here that represents the hyperplane looks like this W here, the sum over the support vectors, alpha I, y I, xi. And the coefficients are only non-zero for the support vectors. Now, let's assume that we had first done a feature transform to our input data before running SVMs. Then, if we ran SVM on the feature transform data, the W would look like this instead, right? It would be the sum over from 1 to n over all the training examples. And now the vectors are just the feature transform vectors instead of the original ones. And B here again would also just be exactly the same, just this new W. And of course, the vectors are again feature transformed. This is just running SVM on the feature transformed data. It give us this. And again, right, this still holds that these coefficients will only be non-zero for support vectors. But of course, support vectors in the feature transform space, right? So I have first map them, and then I look at what is the support vectors of the maximum margin separating hyperplane. Then we would only get non-zero alpha i's for the support vectors there. Okay. Now, okay, so what can we use this for? At least we can make, if we want to make predictions on a new data point, right, we of course had to feature transform it and then compute its inner product with W at the bias B. Okay, so this is what we could do. We could also write out W using this formula here. And, we could also make predictions like this, right? We sum over all the non-zero alpha i's, alpha I, yi, feature transform of xi as inner product with the feature transform of x. Okay. Now, it still looks better to do the first thing here, right? If I want to make a prediction, because, well, this W that I get after feature transforming, well, I'm summing all these feature transform vectors and they have d prime coordinates. So this W here has d prime coordinates, and so does the feature transform vector of x. So computing this first term over here takes d prime time, whereas if I have k support vectors, then the second expression here is slower, right? You have to k times that you have to compute an inner product taking d prime time. So it's still not at all clear what we have gained here, or why would you use the second expression here, but let's hope we can make it clear in a minute. Okay, so this is just SVM with a feature transform. We know that W will look like this, and we know we can make predictions in these two different ways. Now, one really important observation here that we will make use of is that the second method over here, right, the slow version of it, the only thing it uses is actually inner products between feature transform vectors, right? You only need to know what the inner product is between the feature transformed xi and the feature transformed x. You don't need to know what the vector itself is. You just need the inner product. The first method here, you actually need the W explicitly. So here you need to get a hold or handle on the feature transform vector directly. Okay, so let's try to see what we can use that for. So, right, so over here, we only need inner products. Down here, to compute the W, you need to compute these feature transform vectors explicitly and sum them up. Okay, so let's try to see if we can exploit this property. Okay, so here's where the notion of kernels comes in. So a kernel corresponds to a feature transform. So if I have a feature transform phi, then the corresponding kernel is a function that takes two vectors in the original input space, right, in d dimensions, and maps them to a real number. And in particular, this kernel applied to two input vectors x and z just evaluate to the inner product of the feature transformed versions of x and z. Okay, so it's the inner product of the feature transformed vectors. That's the kernel. So what we'll see now is that we could also, just using this definition of a kernel, we can rewrite the support vector machines in terms of kernels. Right, so if we look here, right, this is the optimization problem we need to solve in SVMs. Right, it was this maximization of all the alpha i's and then minus this double sum alpha I, alpha j, yi, yj inner product between xi and xj. And what you can see here, what appears here in this first term, the only thing that depends on the data, the feature vectors, is the inner product. And so also for feature transform vectors, only thing we have here is just the kernel, right? It's the inner product of the feature transform vectors. So maybe the feature transform is the identity if you're just working with the original input data, then the kernel is just the original inner product. But it also, if we're working with a feature transform, then what we would have to do to solve compute the support vector, the optimal solution to the support vector machine optimization problem in feature transform space would be to just use this kernel here, the inner product between xi and xj. Okay, so here's an optimization problem. There's a new optimization problem, and the only thing that involves the vectors is just inner products or the kernels here. Okay, so this is the kernel SVM formulation that we have here. So it's a new formulation where we just have these kernels applied to xi, xj, which are the inner products of the feature transform vectors xi and xj. The bias before looked like this, right? It was you had to take the minimum over all the points in one class, the inner product between w and xi, and the maximum over all the points in the -1 class is inner product between w and xi. And what we can do now, knowing what w is, if you remember, it's the sum over the alpha j's that are non-zero, alpha j, yj, xj. So this means that this inner product here, using the linearity of inner products, is just a sum of these alpha j's not being equal to 0, alpha j, yj, then the inner product between xj and xi, which even for feature transform vectors is just the application of the kernel here. So the kernel applied to xi and xj, and the same goes over here, right? So we can replace this w, use linearity of inner product to turn it into a sum of alpha j, yj, and the kernel applied to xi, xj. So we can also compute this bias using only applications of the kernel. Right, so that's the bias. And if we want to make new predictions, right, we just need to make use of w. And new predictions, then the w again was the sum of all the non-zero alphas, alpha I, yi, xi. And we have to take the inner product between this and a new point x. And so again, using linearity of inner product, we can write this out into applications of the kernel. So the sum again of all these alphas being different from 0, alpha I, yi, and then the kernel applied to xi and x, the new point that we're making a prediction on. So, right, everything here can be written in terms of just the kernel, right? So we actually never need the full feature transform vectors. We just need to be able to evaluate the kernel. Okay. So the entire algorithm can really be written in terms of the kernel, and we never really need the feature transform vectors explicitly. We don't need to know what they are exactly, as long as we can compute these inner products between feature transform vectors. And that's crucially important. And this, if we just solve this optimization problem, this is going to give us the W and the B that corresponds to the maximum margin separating hyperplane in feature space without ever computing any vectors directly in feature space. Okay, so this is interesting. Now, of course, we need to evaluate this kernel as part of this whole optimization problem and part of making predictions. And of course, the direct approach is to, well, do the feature transform on X, do the feature transform on Z, and then compute the inner product. But of course, the time needed to do this is proportional to the number of coordinates of the feature transform vectors, right? So it's going to be d prime, right? So we didn't really gain anything over working directly in feature space, right? Because that also just requires to compute the feature transform vectors and compute inner products. So we need to do something more intelligent here. And the point is that there are actually very natural choices of kernels where it is much faster to evaluate the kernel than it is to transform or to actually explicitly perform the feature transform first. So let's try to see examples of this. So the first example is a very well-known kernel called the polynomial kernel. And here we're going to give the degree 2 polynomial kernel. So what I'm saying here is I'm going to define the function that on two vectors x and z computes their original inner product, so before any feature transform, and then squares that inner product. Okay. Now, of course, right, what I can compute this, well, I need to compute the inner product that takes d time, and then I need to square it, that's constant time. So I can compute this kernel in order d time. Now, of course, it's not at all clear that this kernel here corresponds to an inner product between two feature transform vectors. And for what feature transform does it correspond to this, right? It's not at all obvious that this has anything to do with a feature transform. So maybe this is not really a valid kernel. But let's try to have a closer look here. So if I write out this expression here, the square of the inner product between x and z, then, okay, what do I get, right? I get the inner product between x and z, and I square it. I multiply all the cross terms, so I get the sum over I, the sum over j, xi, zi, xj, zj. And what I'm going to do now is I'm going to group them cleverly. So I group xi and xj, and I group zi and zj. And now the crucial observation is that this here, what I wrote out here, actually does correspond to an inner product. It corresponds to an inner product between the feature transform vectors, where if I plug in a vector x, what I do to it is that instead of having d coordinates, I have d squared coordinates, one for every pair of original coordinates, right? In the first corner, let it be x1, x1, then x1, x2, x1, x3, all the way up to x1, xd. And then I do x2, x1, x2, x2, and then finally xd, xd, all the way down here. Because if you think about it, right, if I take this feature transform and apply it to x, I take this feature transform and apply it to z, then I look at the inner product, then I get x1, x1 times z1, z1. That corresponds to I and j being 1. Then I have to add up x1, x2 times z1, z2. This corresponds to I being 1, j being 2, and so on, right? So this here, the inner product of the original vectors squared corresponds to the inner product of the feature transform vectors x and z, where the feature transform maps any vector to any pair of original features, the product of any pair. Nice. So really, this kernel here that I can compute in d time corresponds to the kernel of a feature transform phi into d squared dimensions, but I can actually compute it in d time. So it's much faster to evaluate than d squared. So if I had performed the transform explicitly, it would have taken me d squared time to transform it. Now, maybe an interesting thing, if you remember some of the previous videos, we saw these polynomial feature transforms where we map input vectors by basically by computing making new features that correspond to products of original features. This is also something we saw together with some of the linear models, linear regression, for instance. We saw that we could sometimes do this. So, and with this perceptron learning algorithm. So this is really a natural feature transform. This polynomial kernel creates all these different features where we have any pair of original features. Now, we could also raise it to a higher power, right? So this is a general polynomial kernel. We could raise it to the rth power. And we can still compute this in d time, at least for constant r, right? Because we just compute the inner product and raise it to the rth power. But what we could also see is that, well, if I take this inner product and write it out, then it's basically the same as summing over r original indices and then taking the product over the x entries with those indices multiplied with the product of the z entries indexed by these indices. Right. So really, if I look at the feature transform that computes for any given x, it computes the combination where for any combination of r original features that have a new feature, that's the product of those features. Then this kernel here corresponds to taking the inner product of phi of x and phi of z. So really what we're doing here is that in order d time, we can compute the inner product corresponding to a feature transform into d to the r many dimensions, right? So think of, say, r is 4, right? Then this is a huge saving if the number of original dimensions is 20, right? And 20 to the 4th is a huge number compared to just, linear in 20. So this can sometimes give huge savings at d time instead of d to the r time. And okay, one can actually also see, if you will, you can add a hard-coded constant c in here. And what happens is that if we write this out, what do we get? This is this inner product plus c squared. We can write it out. This is just what it is. We can multiply it in, right? We get a c squared term, and then we get two cross terms here, like one with c against the sum and c against the sum. So we get 2c times just a single sum. And then finally, we get all the double terms from before. So really, this can be thought of as another feature transform where, well, the first entry of both x and z, I just hard code to a c, because then when I multiply them, I get the c squared contribution. Now, the next bunch of entries, we just have the original vector entries, x1 up to xd, without squaring them or anything. And now the coefficient in front is just, well, you can think of it as having a square root 2c on both x and z, because then when we do the product, it becomes a 2c. And finally, right, there's no coefficient in the last ones. So this is a way to even keep first order terms, if you will, like terms that just includes a single feature of the original ones. And really this C here that we introduce also allows a way to put different weights, if you will, on the degree 1 versus the degree 2 terms in some sense, right? But also if you just set C to 1, then you just get a copy of x1 up to xd, you get the hard-coded 1 and so on, right? So you keep the original features. In general, you can do the same trick if you raise it to the rth power. The only thing that happens is that the degree j terms become weighed by something proportional to the square root of c to the r minus j. So it's a way to give different weighings. Okay. Now, back to the kernel SVM here, right? So everything now is written in terms of kernels. And now the running time for solving this problem, I could say that, well, if k takes t time to evaluate this kernel, right? If I want to evaluate the kernel in 2 vectors, and it takes t time. And if I have k support vectors, then let's try to see what do all these different terms correspond to, just to write out the optimization problem, right? So to prepare the optimization problem, right, we just want to write down what is this optimization problem, right? We just need to know all these values for yi, yj, and the kernel. Well, there's n squared pairs, and it takes t time to evaluate each, right? So we can just evaluate this kernel on all the cross terms, and then we get our optimization problem we need to solve. And once that is solved, once we've solved it, the maximum here, well, I guess we're looping over all endpoints that we're testing, all the data points, and then we're summing here. The minimum goes over n terms, the sum goes over k terms, and the kernel takes t time to evaluate. Now, k, the number of support vectors, is of course at most n. So this is basically it's dominated by the n squared t. And now, so this is this does not really, preparing the optimization problem is faster than computing the b at the end. Oh, sorry, slower. So that's the dominating part, just preparing the SVM problem. Finally, right, making predictions. We see down here, right, when you want to make a prediction on a new point, the sum involves k terms, all the support vectors, and evaluating the kernel on each of them takes t time. So, right, so just to solve it takes n squared times t time to set up the optimization problem, and then just the normal time to solve the SVM problem, right? It doesn't really depend on the dimension anymore. You just get all these coefficients onto the alpha I, alpha j terms. Predictions are done in k times t time, right? So this is what it takes. And of course, we could also have done the feature transforms explicitly. And then, well, it will take d prime time to compute any inner product. So then we get n squared d prime time, which would probably be a lot slower than the first one. Now, predictions would be done in d prime time instead of k times t. And, well, which is better? It's not clear, right? It depends on the number of support vectors and depends on the difference between t and d prime. Right, but in some applications, right, it might be significantly faster if you have few support vectors and this kernel is very efficient. Okay, and so just with this polynomial kernel, right, you can actually create decision boundaries that look like these examples here, right, where you can get these very interesting decision boundaries that nicely, and it does something very non-linear just by using, for instance, these polynomial kernels that we just saw. Okay. Good. So let me just mention one more kernel that's very popular. So here was the polynomial kernel, and this was for a hard-coded constant. So there's also one called the Gaussian kernel. So the Gaussian kernel says that if I have an x and a z, then the kernel, when I evaluate it, should be the exponential function applied to minus the squared distance between the vectors x and z divided by 2 sigma squared for some hard-coded constant sigma squared. Right, and this basically, if you know the probability density function of the Gaussian or the normal distribution, then you would recognize this as this probability density function. So that's where it comes from the Gaussian distribution. Right. So if you think about what happens here, right? So, well, if x and z are close, for instance, if they're the same vector, right, then you would get a 0 here. You would get e to the 0, which would just give you 1. So this would give you a large inner product in some sense. Whereas if they're far away, you get e to the minus something really large, and which of course would give really small inner products, right? So it behaves in some sense like an inner product. Things that are very close, similar, have large inner products. Things that are far away have small inner products in some sense. And maybe a simpler form of it is to not carry around this 2 sigma squared. The way you typically write it is that you write the kernel as the exponential function to minus lambda, and then the squared distance between x and z for some hard-coded constant lambda. Okay, so this is basically the same, just for its particular choice of lambda. Now, of course, it's not at all clear that this corresponds to an inner product between any type of feature transform vectors, but actually one can show that this in some sense corresponds or will correspond to doing an infinite dimensional feature transform. So one can map into infinite dimensions if for whatever that means, but in some sense you can map into really, really long vectors, and their inner products in this feature transform space would correspond to the evaluation of this Gaussian kernel. Right, so you can just plug that in, the Gaussian kernel, into these SVMs, and you can, in some sense, work with an infinite dimensional feature transform without ever going to infinite dimensions. You can actually evaluate it in d time. So you just need to compute the squared distance between the original vectors. Now, maybe let me just conclude by showing that kernels are not restricted to support vector machines. So let us revisit the very first learning algorithm we saw in all these videos, the perceptron learning algorithm, right? So we had this very similar algorithm. If I have d features, maybe a special first one that is sometimes used for the bias, sometimes not. And the labels are -1, +1. you can initialize your vector W just to be the all zeros vector. And then you say, well, while there is a data point that is mispredicted, if you remember this algorithm, meaning that its label is not the sign of the inner product between W and X. So here I'm assuming that the first coordinate hard codes the bias. So it's misclassified. Then we update W by adding Y times X to it, right? So this is the perceptron learning algorithm. We saw it a long time ago, and we've seen it a couple of times. Right, so in some sense, what it's doing here is making this vector W, the hyperplane, more correct on the point X, Y. Right, and then at the end, when there are no more misclassified points, we return W. So the example here is, well, what is one iteration? I have a W here. I look for a misclassified point, and I find this one is misclassified. It's the -1 class. It's being predicted as blue. So now this is the vector X that goes to the point, the feature vector of this point, and the label is -1. So I need to change W by adding -X to it. So I add -X to it, giving me a new W here, giving me a new hyperplane. Right now gets this point right. So that was the basic perceptron learning algorithm that we saw a long time ago. Now you could also look at what happens if I'm running the perceptron learning algorithm with a feature transform. Right, then of course, right, the thing you have to test is, well, if there's something that's misclassified, now what you would do is, of course, you would feature transform your X and compare it to the vector W that you have in feature transform space. So W now is in D prime dimensions, right? So D prime coordinates in the feature transform space. If you find such a point, well, you would add Y times this feature transform vector to W and keep going. Now, what you see here is, right, the update rule for W is that W at any given time, it's just a sum of feature transformed input vectors, right, multiplied with our labels Y. And you're only computing inner products against W like we do up here, right? The only thing we're doing is computing inner products against W. So we can actually do it using kernels. So let's try and see. So this is a new way of writing the same algorithm. So I'm going to write W as a list of vectors, W list, with a list of coefficients A, which are the A list. And then I'm going to make this. So basically my test now for a misclassified point is, well, I'm going to sum up all the points in my list. I'm going to take the coefficient that I have on it, multiply it with the vector, and then I'm going to compute the inner product with the feature transform X. And if this is different from the label, I append the feature transform vector X to the W list, and I append the label Y to the A list. Right? This is the same algorithm as before. Now, using linearity of inner product, I can also move the sum outside. So now the inner product goes in here. So I sum over all the individual elements of the list. I take the coefficient, and I multiply it onto the inner product between the ith element in the A list, in the W list, and the feature transformed X. This ith element is just some original input point that was added to the W list, but being feature transformed. Okay. Now, instead of doing that, right, I could also apply the kernel here to the original vectors and just store the original vectors in the list, right? This is the same. What I'm saying is I'm just computing, all I need to do is I want to compute this inner product between feature transform vectors. Over here, I do it by adding feature transform list vectors to the W list. Down here, I'm just adding original vectors to the W list, and now I need to compute inner products, and I do it via the kernel. So this is, again, this is the same perceptual learning algorithm, just using kernels instead. Right, so I can also implement this with kernels. So now I never transform anything into feature space. I never go into the feature transform space. I just stay in the original input space. And for predictions, right, it's the same thing. I just need to compute inner products with W against a new vector. And using linearity again, I can just sum over all the entries of my W list. I take the coefficient in my A list and multiply it onto the kernel applied to the element that I stored in my W list and X. Right, so I can actually use this together with the perceptron learning algorithm. And now a really interesting experiment is to try what happens if I run the perceptron learning algorithm together with the Gaussian kernel that I just showed you before. And here is 3 different plots of running this on a data set. Here you can see there's some red points up here in the upper right corner, lower left corner, and also a few in the lower right corner. And then we have some blue points as well. So what I did here was I tried to run the perceptron learning algorithm. I ran the pocket version of it. So even if it doesn't terminate, I just keep track of the highest accuracy hyperplane that I saw throughout the execution of the algorithm. Right. So this is also a trick we saw early on when we looked at the perceptron learning algorithm. Right. So I just run this loop where I look for misclassified points, and I just keep track of the best W I've seen throughout this execution. Okay. So what I can see here is if I run it with different values of lambda, this lambda up here in the exponential function, I get different decision boundaries. And what I've plotted here is the color intensity really, in some sense, illustrates how close I am to the two different classes, right? So white is exactly on the hyperplane, and if I go on the blue side, I move more and more towards, I guess, the blue class, and on the other side, I move more into the red class, further away from the hyperplane in feature transformed space. And you can see here, right, that varying this lambda gives very different results. And actually here, lambda of 1 gives a really interesting and nice encapsulation and decision boundary around the red points and the blue points. And it looks like a kind of plausible explanation. And, you know, as you increase the lambda, you get different kinds of decision boundaries. Right. So this is a very interesting example of actually how you can if you just plug in this kernel, right, the thing that you compute actually corresponds to these curves instead of hyperplanes and straight lines. Right. So this is really a way of getting a much more power out of these linear models again. Okay. So maybe let's just conclude with a couple of considerations that are worth taking into account. And one is that we saw in some of the learning theory videos that, well, the complexity of the hypothesis set matters for generalization. And low complexity is better. And in some sense, right, we also had this argument early on that maybe one should try to avoid having too many features in the feature transform vector. Right. So for instance, it might be a bad idea to use a polynomial kernel with a too large R. And maybe also a Gaussian kernel mapped to infinite dimensions actually seems really bad, even though on this previous these plots it actually looked kind of reasonable. There is this theory that can actually explain why it still works, even though we go to infinite dimensions. But it's beyond the scope of these videos that we're making here. But you can there are actually theoretical results that explain why it works still. And of course, right, there's just one thing left to do at here for the polynomial kernel, right? This is hard-coded constant C, and for the Gaussian kernel, there's the lambda. So how should you choose them? And this is just maybe a recap to previous videos, right, when we saw validation as our technique, right? So what you could do is set aside a small validation data set, maybe 20% of the training data, and then just try multiple values of C and lambda and go with the one that works best on the validation data set as we saw earlier. Right. Okay, so this concludes what I wanted to say about kernels, and in particular in the context of SVMs.